So in this video, we will cover how to arrive at linear regression optimal equation using probability and statistics. So consider we have a dataset D, sorry, dataset D with points xi and yi, where xi are the independent values and yi is the dependent or the predictor we have to predict. Sorry. So xi belongs to xi is a real value with a d-dimensional real value, and yi is a real number that we have to predict. So as we saw in the first part of linear regression, so our predictor yi hat is given by the equation w transpose xi plus b, where uh, W and B are the slope and the intercept of the line or a plane. And our objective was to find optimal value of W star and B star. That's the optimal value of for which we would minimize these sum of squared errors. yi minus yi hat whole square. This was our objective, and this can be rewritten as argmin of find the value of w and b for which I equals to 1 to n yi minus w transpose xi plus b and this whole square. As we can see, the yi height is nothing but w transpose xi plus b, right? I substituted it. So this is the sum of squared errors. And for this, essentially what it tries to do is, if my data points are in a two-dimensional, if they are like this, then essentially it tries to find a best fit line which is as close as to the data points. Best fit line. And my loss is given by this is the loss, and this is my x-axis is defined as error. So error is nothing but yi minus yi hat, and the loss is yi minus yi hat whole square. So it will be a, a parabola. So excuse me. So we saw that my error epsilon I is yi minus yi hat. It's given by this equation. So what linear regression states is to derive the probabilistic interpretation for linear regression, there are some assumptions. The assumptions made by linear regression are: the first one, linearity assumption. What it means is, we can, like as we saw here, we can fit a plane for the data points, like we can fit a plane or the line linearly with the data points. That is called as linearity. Second assumption is, sorry, come on, And the second assumption is we saw that uh, the error is given as epsilon I is given as yi minus yi hat, right? So the second assumption of linear regression states these errors are normally distributed. These errors are normally distributed with mean 0 and variance sigma square. Next, third assumption is errors are independent of each other. Means there is no correlation between the errors of each other. Next assumption is the values for the features xi are independent of each other. Means there is no correlation between the features. The last assumption is the errors are homoscedasticity should be maintained for the errors. Homoscedasticity. Errors are homoscedastic. What it means is variance between the errors are uniform. What it means is when I plot the errors, the plot should be like this. The variance is constant between the errors. This is called as homoscedastic. And the other is if the errors are like it's spread out like this. Imagine this is heteroscedastic. So my errors should be spread. My errors should have homoscedastic in nature. So by taking these assumptions, we can proceed further in deriving the probabilistic interpretation. So as we saw, my error epsilon I has a normal distribution with mean 0 and variance sigma square, and my uh, epsilon I is nothing but yi minus yi hat. So, and this can be rewritten as yi equals to epsilon I plus y hat, which is nothing but w transpose xi plus b plus epsilon I. And for this, as we know, my epsilon I is defined is having a distribute. No, it's normally distributed with variance 0 and sigma square. The distribution of yi can be written as a normal distribution with the mean of w transpose xi plus b and variance of sigma square. Why this happens is, imagine if I have a distribution for z is z is normally distributed with variance 0 and sigma square. If I add a value of 10 to all the data points, then my distribution will become with a mean of 10 and sigma square. So using this property, we can find the distribution of yi having uh, a mean of w transpose xi and variance of sigma squares for its Gaussian distribution. And we can change the yi into a probabilistic interpretation, like probability of yi given xi with the parameters w and b will be having a normal distribution with mean w transpose xi plus b and variance of sigma square. As you can see, this is a conditional probability. So for a given value of xi and parameters w and b, I have to find yi. That's what it states. And we know the likelihood representation or function for the above equation is, what is the likelihood for the value of w and b? We can find yi's or the value y when given x for a given xi. And sorry, and we know the errors are independent of each other, right? So having the conditional independence property over here, applying the conditional independence property, conditional independence, what it states is, if I'm having data points x1, x2, x3, so on, x2, x3, so on, xn, then this probability can be written as probability of x1 into probability of x2 into probability of x3, so on, probability of xn. This is the conditional independence property. Thus, using this property for the likelihood equation, we can rewrite it as equals to product of the individual properties. So product of from I equals to 1 to n is uh, yi for when xi is given for the parameters w and b. And when we find the probability distribution function for the above equation, distribution function PDF of above equation, this can be rewritten as the likelihood function becomes product of all terms 1 by square root of 2 pi into sigma exp of minus yi minus y hat, that's nothing but yi minus w transpose xi plus b, this square divided by 2 sigma square. This equation I got it from here. Probability density function. Where is it? Oh, sorry. Probability distribution function, sorry. Where did I find? I'll attach the link where I found that equation. Now, now we have to optimize this equation. So for value of W and B, I have to find optimal W and B for the above equation. So finally I found this equation. This is the PDF of the normal distribution. So using this equation, we have written our likelihood function equation as like this. Now, for this above equation, we have to find optimal W and B. And this can be rewritten as find optimal W star and B star. Those are the optimal values for W and B. We have to maximize them. Argmax of W and B and same above equation. So for my likelihood equation, I need to find the W and B which maximizes this product. Now we can convert this to a monotonic function. So how we can do is we can apply log to our likelihood equation. So this becomes argmax of W comma B log of for my likelihood expression. And this whole equation can be rewritten as argmax W and B log of my product term I equals to 1 to n 1 by root 2 pi sigma exp of minus yi w transpose xi plus b, this whole square divided by 2 sigma square. We know the properties of log, right? Like log of a into b can be written as log a plus log b, and log of exp of x is x. So using these two properties for the above equation, we can finally like split this whole part. We can take this log inside, and then this log of exp will become this inside term. And here sigma is constant. In this whole equation, the constants are like sig variance. The only variables are w and b. So, and we cannot maximize sigma over here, so we can ignore that constant, and the whole equation can be rewritten as r max w comma b sigma I equals to 1 to n. This inside term only will remain minus yi w transpose xi plus b whole square. And maximum of minus is nothing but minimum of positive term, right? So this becomes argmin for a w and b I equals to 1 to n yi hyphen w transpose xi plus b whole square. This is nothing but our sum of squared errors. This this is the probabilistic derivation for our linear regression.